Yeah, fantastic. So yeah, we'll be talking about what we've been up to, what we're planning to do over the course of the next year, taking feedback on that based on what you guys want, and we will also go into lots of gory detail on the tool changing systems, which is, I'm sure, what most of you guys are here to do. Yeah, V6 is one hell of a moving target. Claire, can you give me time checks? When I get to half an hour, do you want to just give me a wave so I don't ramble on? I have a terrible reputation for rambling on. So V6 has been like a moving target over the course of the last 3 years that it's been out for now. Part of V6 is actually the same as it was when it was launched, so everything's made on machinery. The designs for most parts have been updated in one way, so there's a lot that's changed about these. Into that, the heat breaks have vastly improved, and we've got a lot going on with our machining ops, and we're able to improve the surface finish, which is really critical on the inside of the heat breaks, i.e. the part in which the polymer transitions from solid to liquid, goes through that kind of rough, sticky melt state. And so the internal surface finish has been improved by a whole bunch on the inside of the heat breaks. Nozzles as well, via the same upgrades machining hardware that we've been bringing on board. The concentricity surface finish and the degree to which plastics sticks to the much reduced. The more particle better, so more conductive. I think we'll be switching from copper to thin, less conductive, but because the cartridge is much thinner, that means that the cartridge will actually be more conductive because it's a better ability to transfer heat to the inside of the cartridge effectively. The heaters are improving drastically, both the geometric tolerances and the ability to be consistent in their heating power throughout, and a higher MTBF, like mean time between failure on the heating cartridges. So you get much longer lifetime out of heating cartridges as well. And yeah, just drastically scaling up production. We make tens of thousands of V6 every month, tens and tens of thousands. And the bearing issues, I'm glad to say that we were having with Titan, that some of you, put your hands up if anyone had a broken bearing in a Titan. Oh, sorry, dude. Yeah, that's all fixed, and everyone should have their fixed parts sooner rather than later, so that should be done. We are, pardon? No, there's no one in here. So yeah, we're working on some high temperature materials, aerospace grade stuff, and we'll be releasing some highly modified, like all-10 competing materials over the coming year, and we've got nozzles to match with those, high temperature copper alloy and blocks. We're introducing water cooling. A lot of people ask me, like, what the hell is water cooling for? Isn't it massively overkill? Yes, in normal circumstances, but if you're printing inside of a heated chamber, then water cooling makes perfect sense because it allows you to transport heat out of the build envelope and transport cold water back in, which lets you cool something that is being heated inside of a heated chamber. Because you obviously can't cool something with a fan when the air is hot, it just doesn't work. Scaffold Snatch just come out, and yeah, we're up to tool changing. Coming soon, I will whiz through these. Super Volcano, which is a volcano but with more flow, kind of 2 to 3 times the amount of flow. Or similar, which is a hot end where you have 2 hot ends at angles and they rock as such. The new version of Titan Aero V2 Mini, which is kind of our focus over the coming 3 to 6 months, making something that's kind of an integrated extruder and hot end all in one small, concise, very lightweight package. So we should be able to realize 30 to 40% volume mass reductions in there. We've got a new nozzle coating coming out that is both high temperature resistant, and plastic doesn't stick to it nearly as much as bare metal. It's not perfect, and it's not, it's by no means is plastic just going to never build up on your nozzle, but the amount of buildup and the magnitude of buildup is much less. Because of the machining upgrades that we've brought in, with higher concentricity and so on, we can make nozzles even smaller. So putting out 0.1 millimeter nozzles as well. So if you really want to play that game, because some people are actually using the 0.15s for really quite useful things like miniature figurines and things like that. So we already do 0.15 millimeter nozzles, which are quite tricky to use. But going down to 0.1 should be the next challenge if people want to play that game. Higher temperature sensors. I know we already do thermocouples and PT100s. We're looking at something that is basically equivalent to a high temperature thermistor, but better. More to come on that. The very power beds should finally be finished because we're finally managing to employ an electrical engineer. So they're the beds that have we don't spread the power evenly over the bed because beds cool more in the corners and at the edges than they do in the middle. We kind of took a FLIR image and then we do the inverse of that FLIR thermal image so that you pump more power to the corners and edges such that you kind of bend back out the other way, that temperature gradient. So you can, if you're printing a big plate of parts, you can print parts right on the corner and it don't fall off, which is an eternal problem with normal heated beds that use an even power density across the beds. And what currently codenamed Mordor beds, which are just absurdly high power heated beds for high temperature applications like printing, where you have to have your bed running at 200 degrees centigrade for certain materials. So those are on the way. Sorry, what most of you guys came here to see, which is the tool changing 3D printer, which is something that's been a really long labor of love for us. We've been probably doing this for the last 18 months, 2 years, and it's finally getting there. So it's really great to see it kind of come to fruition. It's not a fully complete 3D printer, as most of you that have been to Expand have been saying. We're still figuring out exactly what it does and doesn't include, but what is clear to us is that we will be shipping it as standard without any tools. Our reasons for doing so are that everyone has a different application, and printheads are so application dependent. And the really unique property of having a tool changing printer is that you can really tailor every single printhead so that it really does its job very, very well. So we won't be shipping it with any tool heads on it, and you can kind of pick and choose. We hope to have prepared and ready built printheads that you guys can just kind of buy off the shelf for, if it's a V6, it'll be very little above the cost of a V6. And we won't be shipping it with electronics. So David Crockett is in the audience today. It's good to have you. We won't be shipping it with electronics. We will be recommending and supplying a reference implementation of electronics that is implemented on Duet and the firmware, so that people can see what their electronics and firmware should be doing. And we would encourage anyone that just wants to get up and going to use a Duet. But we also want to encourage firmware and electronics developers of all shades to come along and build electronics and firmware that is able to work with systems like these. So we just are trying to enable people to implement stuff. And that's the whole objective of this release, is kind of enablement as a reference platform to let people build stuff off of. We said we need enough pre-orders. We now have enough pre-orders. more than enough pre-orders to start making them. So it will almost certainly be going ahead. So that is no longer a requirement. It will cost probably more than £1,000, £1,000 to £1,500, and that's before, that's without tools and without electronics. So it's not cheap, but it is very well made. And there are expensive parts that are going on there, genuine Highland rails, and so on. Please fill in the survey if you haven't already done so. It really helps us out to know what you guys want to do. So I've been doing a lot of learning on motion control, especially since the whole big box debacle with the Z-axis. There's some really awesome resources out there there's a sub-department of MIT called PERG, and they have a website called Purgatory, which I think is quite funny. But yeah, it's called the Precision Engineering Research Group, and they've got some amazing lectures. And the guy who wrote most of the lectures, Alexander Slocum, has also done an incredible book, Motion Control. I forget its exact name, but it's a real read if you really want to get into the woods on motion control theory and practice. I recommend it, and this is kind of the fruit of that. So we have a motion control system that is entirely mounted to a single aluminium tool plate. It's a solid piece of machined aluminium tool plate. Tool plate is extremely stiff and also extremely planar and flat, which is a good reason for choosing it in and of itself enough. But yes, the tool plate is very flat, but really what defines the flatness of the whole top plate is that you've got 5 struts of aluminium extrusion. And as long as you cut those 5 struts of aluminium extrusion to exactly the same length, when you bolt down the plate onto those extrusions with a very high level of assertiveness, that plate will end up flat because you're pulling down everything to an equal height. It will enforce planarity across the whole surface of that top plate. So that's your kind of reference plane. And then from that plane, you add your stuff. So you can see really nicely. So we've got 2 belt paths, and we've got the other motor. This is one of the XY motors. They're both XY motors because it's a core XY system. But the other XY motor is on the other corner. And it's spaced slightly further off. So throughout the whole system, everything is mounted on standoffs of this sort in one way or another. So you've got the idlers, machined idlers, and the spacers. Spacers are different length throughout. There are basically 2 heights, and everything is mounted on a spacer. And as long as you, again, make your spacers of a known and consistent length, which is very easy to do, not a hard job as a machinist to get something exactly the same length each time. That enforces absolute planarity across the entire motion system. With the new version that we're showing out there, compared to the previous V1 version that we were talking about at Midwest, we've now also added the Z motor. So the Z motor also backs onto that plate. The back surface of that motor is against that face, which just kind of increases consistency across the all 3 axes of the motion system, and ensures squareness and perpendicularity across all. The belts, we're using these new fancy belts from Gates. I forget what the exact product code is, but you'll see these ones look a bit reddy brown. They are the teeth on them are faced in kind of nylon non-woven fabric, which reduces the rolling resistance as they travel across the belt, across the pulleys. But the nylon coating, and this is the reason why we chose it. So it's designed to not shed dust, but the tooth facing also stiffens up the tooth. So the tooth has to engage in the pulley, and as you apply a force to the belt, the tooth is obviously going to deflect in some way, and the nylon stiffness of the belt, which is a flexible part, and it means that you have more control assertiveness, so you can get slightly higher accelerations and deflections. Gates are also really good at putting a lot of aramid, which is the backing fiber, which creates the stiffness of the belt in terms of it keeping a consistent length, which reduces stretching. We've done a lot of playing around with different types of belts. We even tried making our own. These are the best we found by far for their stiffness, but not only their stiffness, but also their damping rate. So they're what we call like a loss coefficient, which is the, as you go around a corner, you're all familiar with this. You swing a corner at a high acceleration, you turn 90 degrees, and you come along and you produce this like damped sinusoidal oscillation as you go around the corner, and that's what people call ringing or ghosting. Lots of different words for it, but it's that as you go around a corner. It's not just about having a very stiff system, because if you have a very stiff system, yes, it won't deflect very much, but if it's stiff and also quite resonant or has a high degree of restitution or basically efficiency in bending of it for a very long time, which you don't want. The ideal thing would have a very stiff belt, which also has a very high loss coefficient. So it dumps that energy very quickly when it stretches, goes boom, and that's all you get. So you're always going to have some deflection, which you want to minimize through stiffness, and you're always going to have some ringing, which is that back and forth motion. You want to remove as much of that as you can by increasing the loss coefficient such that the belt self-damps very quickly. And these belts are very, very good. Tool picking mechanism. Oh, yeah, and high wind rails. Sorry, before I get off of this, the high wind rails with a very slight amount of preload. Preload in bearings is about when you make the balls ever so slightly too big for the gap that they're going into, and you end up squeezing the balls slightly so they get bent out of round, but only in the elastic regime, not the plastic regime. So they're just like a bouncy ball. It's just slightly squished in there. So there isn't actually any clearance or rattle in there. So you can buy high wind rails with a variety of different clearances and preloads and so on. If you are going to buy your own high wind rails, or in fact any linear ball bushing type device, get them with a light preload rating, which means that you'll have the balls squished by, I forget how much it is, but I think it might even be sub-micron amounts. But they're just ever so slightly pinched in there. And that means there's no rattle. But if you get a very high preload, i.e. the balls are quite squished, you end up with apparent stiction, effectively. So you end up with like a small amount of stickiness. That's fine and dandy in CNC machines with huge amounts of a very high amount of, what do you call it? What's lost my mind? Control assertiveness, basically, in your motion control loop. But if you have that in a belt-driven system, you get this kind of like stick-slip kind of apparentness. So get a slight preload to eliminate any rattle or lash, but only just a tiny bit. Okay, on to how to pick up a tool head and why. I want to see how many of these slides I have left to do, because I know that I'm going to be shouted at if I overrun here. No, we're good. Yeah, how to pick up a tool head. And this was the longest part of this whole research phase. Magnets, which are big, chunky, expensive bits of electronics. They're really nice because it's basically a permanent magnet that you can electrically switch on and off, or even reverse the fields of. So that's nice because you don't need a large amount of power to keep them running. So a permanent magnet, not permanent magnet, a normal electromagnet. Yes, we could have used one of those, but they use a lot of current and they actually generate a fair amount of heat compared to the amount of kind of grab that they have. So we didn't go with an electromagnet. We ended up not going with an electropermanent magnet because again, there's just like a bit too much bulk in them. They're very hard to source, and they're kind of heavy and awkward little beasts. I say little beasts, they're quite big actually. So we didn't go down the magnetic route. The one that I was saddest to see go was, and this is inspired by how they do panels in automotive factories. So you have the whole robot arm, and then you might see these like four-armed little things with little rubber grommets at the end. What those actually are is pneumatic suckers. So they pop them on, and then they have a vacuum pump, and they suck the body panel onto the suckers, and then can move it. They're nice because they're like the Bowden system, if you like, of actuation devices or pickup devices, because you don't have the power on the toolhead. So you move a lot of weight and all the motors and things that are doing all the electromechanical work. You move that off the printhead, which is nice because then you just run a tube up to your printhead, and we were going to have a compliant kind of closed cell foam gasket, and then that hopefully would go over to the toolhead and suck onto it, and it would pull itself into place, and then the kinematic couplings would then kind of seat themselves, and we were hoping that the gasket would have enough kind of compliance to be able to be kind of squished into alignment when the kinematic coupling came into play, which did work. That's handy. The issues really around vacuum pumps, the amount of noise they make, the amount of cost they add, and there are also other concerns that we had around how long is the closed cell foam going to last through multiple repetitions. Never actually tested that to death, and also with like contamination, like the kind of filth that just generally comes off of printers, and like those slight strings, and even those strings that kind of float off. Eventually probably going to break a seal somewhere along the line. And what you have to realize is in one print, you're potentially doing thousands, if not tens of thousands of pickups and drop-offs and acquisitions of toolheads. So you have to make this thing fiendishly reliable. Otherwise, it's going to fail. And when it does fail, it's really catastrophically bad because the toolhead falls off into the print, and then it's really not. It's not good when the tool heads fall off. I've been there. It's bad. So we're concerned that the vacuum, if you broke vacuum seal, then you'd be in a really bad way. And then there are kind of clicky-clacky latching mechanisms, like kind of like a ballpoint pen. You can like bistable, so you might be able to drive into the printhead and have something that kind of clicks on, and then you kind of force yourself off in some way. You would have some kind of slot that you could slot into and pull off of. Those ended up being kind of large and bulky and a bit clunky, and also many of them at times they're difficult to implement in a way that doesn't interfere with the kinematic coupling, which is the precision location device that we're using. Before I go into those, what we did end up going with is a servo-actuated method. When I say servo, I really do mean those little RC hobby servos. A lot of work done on them, like something that's been optimized again and again and again. And it's shocking how good these little devices are, how little and how very small package. They move quickly. You can control them easily from electronics really, really well. They're just really nice packages to use, and they weigh nothing. They're so light that they're almost of negligible weight when you consider the weight of the other masses in the system. So effectively, from a mass perspective, they're almost free. They weigh so little. So those is the actuator. Here inside, you see. So what we have is the second one up. That is the slot into which a kind of T-shaped bar is inserted, and each bar has on it kind of ramp, so it kind of screws into the slot effectively. So actuated by the servo and the gears, that bar gets inserted into that slot. It kind of screws into the slot. And the bar, and then you have the, which is actuating that T-shaped bar, and the drive shaft can slide in its bearings. So there's a clearance fit in its bearings. It can slide in those, and if spring is biasing it back. So it goes into the slot, it rotates and screws in, and it's forcing the tool head back onto the precision locating elements, which are these little V-groove things we'll get into in a moment. The nice thing about that is it's a positive lock, and it's possible for the printhead to knock it off. And so catastrophic isn't going to fall off is because it has a stiff but nonetheless present kind of spring in the system. You can crash into things. The hot end can give because it kind of, the spring flexes a little bit, and it snaps immediately back into coupling, so you can go on to locate it. So kinematic couplings, into them in too much detail because the theory is moderately complex, but there you have 3 balls that sit in these 3 V-shaped grooves, and what each groove and ball gives you are 2 contacts that go through each other like that, and you space them out, and then each of the contacts removes 1 degree of freedom. So you have 2 per set, and then by the time that all of your balls are in contact with all of their locating V's, you end up removing all 6 degrees of freedom. So that's the 3 degrees of translation, and then the 3 degrees of rotation as well, all get eliminated through this coupling system. And because you only have 1 doing each one, you don't get any kind of, it's not like a table with 4 legs that can rock. There's only 1 location. Once you apply a preload, which is what causes them to settle, there's only 1 location that they can acquire within their slots. The balls can acquire within their slots. So in our current implementation, the balls are on the tool head, and they get forced in there. You'll note that there's a little bit of grease on each one of these. We actually use lubrication on them to cause them to settle. The ones that you see up here are kind of mangled aluminium jobs, but on the final ones we'll be using round hardened steel, tool steel. So you really want to enforce, you don't want any wear or deformation there, plastic or elastic, and you do want the elements to be able to kind of slip on each other such that they can settle very efficiently and effectively into their groove rather than catching. Aluminium is just about the worst material you can make a kinematic coupling out of. It's easy to machine, and we have it lying around. Yeah, electronics. Claire, is that half an hour? Okay, cool. I think that's good because we're about halfway through. I reckon, just about. Electronics, we use Duet, complete with the expansion board. 2 main reasons for that. One is that it's one of the very few boards out there that has enough I/O to drive all 4 hot ends, and have I/O left over for all of the other stuff that's going on, such as the servo for the outputs and bed leveling and so on and so forth. You've got tons of I/O by the time you add an expansion board. So that's great. The second main reason is scriptability. So slicers are nowhere near smart enough to be able to drive all of these things and have a best rudimentary scriptability. Whereas in the Duet system, you have basically everything is G-code, and you can have G-code nested within G-code. it means that ultimately the slicer needs to know nothing about the hardware. So all of where does the machine pick up the heads from? Where does it drop the heads back to? Where does it go? So even all the wiping and going over the brushes and turning on the vacuum cleaner, even all of these things, that they're not at all to do with the slicer. The slicer simply issues T0, T1, T1, T0, etc. And the movement G code, where to go and spit out plastic. And the duet and its firmware takes care of literally everything else, all of the wiping, the priming, purging at the end, turning on the vacuum, actuating the coupling. All of these things are all taken care of by the firmware, which is super awesome. So yeah, well done for that, David. On to calibration, which people always ask me, and they're like, God, is it going to be a total nightmare to calibrate this thing? No, and we have a really neat system for doing it. Vernier calipers, there's like things, not the new digital ones and not the dial ones, but the old school ones where you have the little lines that you have to read off and find the two ticks that are most well aligned. Uses visual acuity to increase your ability to resolve small amounts of relative distance. What we do is basically print vernier scales, and we print vernier scales on the bed in X, in one material, so in this case white, and then we come along, so you load tool 0 up with white, you come along, print your bunch of lines and ticks in white, in both Y, so on the bed you kind of have, if the screen's the bed, you have 1, 2, 3 in Y, 1, 2, 3 in X, and then you come along and you print your tool 2 with your separate colors that you can see on here, and then you basically go along and you look for the two lines that are best lined up, count the number of lines they are away from the center point, and so once you understand the system, are practiced at looking at the lines and finding the lines that line up the best, you can, in one print, and bear in mind one of these little prints takes, I don't know, something like a minute or two to print. You print one set of those and you can easily read off all of the tool head offsets and put them into the firmware very, very quickly. Print another calibration pattern just to verify, and you're fully calibrated for tool heads relatively in XY. It's super easy, and it works with not just tool changing, but any type of multi. If you've got more than one nozzle in the system, it's a really great way of doing it, and I recommend it. Thing number, whatever that is written up there. And then to get Z, you get it to within ballpark, and then you just peel off the calibration strips and you caliper them for their relative heights, subtract the distance away to find the offset. So not nearly as much of a nightmare, especially once we figured out this vernier calibration routine. It makes a lot of difference. It's super quick. Would recommend it for anything where you have more than one nozzle. So yeah, then we have the fun part is all the things we can now do with this system. The one on the left is nearly finished. It's mainly a software task to get it going, but it's a Raspberry Pi Zero with the new version of the Raspberry Pi camera, which has a macro lens put on the front of it, so it can focus at very close distances at a high magnification. So it's effectively a microscope, and we can go along, move the head into position. So our bed is 300 by 200, and so we divide the bed up into 6 100 by 100 chunks, and we go along, and you can, for every single layer, you grab the print head, you go over to each one of your 6 100 by 100 squares, and you snap an image of it. So in one layer, you grab the tool head, 1, 2, 3, 4, 5, 6, take a picture of every one of those squares, and then the Raspberry Pi Zero, all it has to do is upload those to, at the moment, just a local network drive. From there, we are writing a script that stitches together those 6 images to form one image. So you take your 6 snaps, stitch them into one, and bear in mind with the Raspberry Pi 2 camera, I think it's a full HD camera, and the macro lenses work really well. So you've got 6 times full HD image of the bed. Then you obviously reconstruct for every single layer, each slice of your print, and so you end up with 1 image per layer. You run those through, and you keep these as PNGs, so they're very large in size, but then you run those all into, you turn them into a video and encode them using an FFmpeg, which is basically using, you turn all of those images into a video that plays back the whole set of layers. It gives you a very good rate of compression across your frames, so you end up storing an entire print into a very small video, and you can store it as a lossless MP4 format, and so you get a very high definition capture of every single slice of your print being printed, so you can go back and fully verify that your part was printed, that every bit of infill finish, even if you were printing an opaque color, you can basically go back and look inside throughout the full length of your print, see that every single bridge made it, or this one failed, that every bit of infill was made, that all your adhesion across the bed was correct or it wasn't, and so on and so forth. So really nice for verification. I'm rambling on, so go short for time. This one here is the one in the middle, is the first go at our flexible extruder. We're actually scrapping all of that. We're remaking the heatsink and bringing the drive system right down. We're making a special heat break that will go right up into the drive wheels of a kind of Bondtech-esque dual drive wheel system. And the nice thing about flexibles is they don't require much force to drive, so you can use a very small motor to drive these little wheels, and also flexibles don't require nearly as much cooling as PLA, so you get away with a much smaller heatsink on there. So it ends up very lightweight, because you've gotten rid of quite a lot of heatsink and general bulk. You've gotten rid of quite a lot of motor as well, because you use something like a NEMA 14 or a 12, and it's dual drive, print flexibles really, really nicely. So that's that tool. Then we have the Volcano on the way, which is basically the same as the V6 one you've seen out there. It's got a longer fan duct. So those are a lot of fun. What we want to do in the future, add laser beams, lasers for part marking with diode lasers. We also hope, I really want to experiment with using the laser to perform subtractive edge trimming. So just coming up and cleaning up edges, cutting holes to tolerance maybe, those sorts of things. I don't know if a diode laser is going to be suitable. I have a lot of questions about what it's going to do to the layers below, and yeah, but interesting to experiment with, because unlike the next one along, which is subtractive, like true subtractive milling or light milling, you don't have any forces applied to the tool head. So if you can make it with lasers, that's pretty cool. But yeah, one of the ones we're focusing a lot on is a very, very, very lightweight milling head on there. So you can come along and every 1, 2, 3, 4, 5 layers or so, you can come along and cut parts to size. And if you do that layer-wise, it's nice because you only have to cut a very small amount of plastic, so very low cutting forces when you're machining it by each layer. And you also don't generate a lot of swarf, you're not generating a lot of forces, noise, you don't require a lot of power, so you can get away with this tiny little milling cutter and a very lightweight, but still high quality motor. You need to go at very high RPMs in order to cut plastic effectively, and you don't want any amount of imbalance in your motor, otherwise you basically vibrate the head to death. Inkjet, which I really want to do to try inkjetting release agent onto support material. So on the top surface of support, you jet something that stops the next layer on top sticking, and that means that you can separate the two effectively. One that I'm really excited for and is going to be reasonably easy is pick and place, so that you can add parts to your prints automatically throughout the course of printing. And the way we envisage this working is that the first thing you do is print on your bed a small sort of dock off to the side, a part holder, if you like, into which, so it's a kind of jig or fixture, you know, for if you want to put a nut in and you want to lie that nut flat onto the print partway through the print, you would make a little hexagonal hole and you pop your nut in. Or if it was some sort of screw or something else like that, you build a small jig or fixture into which you can insert that part that is to be inserted later. You put it in its final orientation into that part. And you leave that printed fixture on the bed probably, or otherwise fixture it onto the bed. You then come along with your pick and place head, and we're looking, I don't know if everyone's seen those robotic grabbers that basically use a balloon full of coffee grounds and a vacuum pump, so that you go over to a part with this balloon that's full of loose coffee grounds, and then you turn on the vacuum pump and it causes the coffee grounds to kind of contract slightly and stiffen right up because you suck all the air out of the balloon that the coffee grounds are being. I think I'm explaining this really badly, but effectively you've got this way of picking up very irregularly shaped parts with this conformal grabber that you've created. Maybe I'll show you a video at the end if we've had time, which, I don't know, second to last slide, and so we'll go into that after questions. Yeah, so maybe you have a grabber like that, or maybe you just have some kind of standard jaw type grabber, servo actuated or otherwise, and you can print appropriate jaws for the grabber. So because you've got the 3D printer, which is great, you can print yourself the jaws, and you can print yourself the fixture. You can come along and grab the parts off of the jig and fixturing, drop it into the part, and then continue printing, trapping the parts inside. Yeah, closing thoughts. Slicers and generally the tool chain as a whole could do with coming a whole bunch of the way forward. Even right down into CAD, which is quite bad at realizing kind of multi-material parts and the like. They're kind of hard to design for, but you know, I really want to. I have this part in mind once we finish the flexible extruder where we have a wheel, print a whole wheel with the tire around the outside in some kind of flexible polyurethane. We have carbon fiber reinforced nylon for the kind of rim hubcap type thing, and then have in the center of that would have a plain nylon ball bearing or bushing. If it was a ball bearing, it would be really cool because it would be multiple parts printed in place, and you come along with a soluble support to support the underside of your hubcap and maybe also your ball bearing, if indeed you print it. And that's like a single complex product that you could manufacture in one shot and would come off of the printer as a fully assembled, ready to go product that comes straight off of the machine. And we could even end up inserting in bearing in place. We could insert bearings into it using the pick and place system. So yeah, fully assembled, ready to go parts printed as one. It's just a bit beyond what CAD was designed for, what slicers were imagined for. They don't need to come far, I don't think. It's somewhere how it handles most of the stuff that the print has to deal with. Much of us have come in, so you mentioned this more, is that, yeah, the whole thing flat packs very well, and that's not by accident. Yes, you can take the whole top plate, have it assembled and built, and you can then flat pack the rest of the printer on top of it. You take it out of the box and you have just the 5 uprights to bolt into place and bolt the bottom frame on. It's ready to go. So yeah, it's really easy to assemble. Yeah, questions? Gosh, finish 10 minutes ahead of schedule first. Yeah.
So would it be possible to automate this calibration procedure with thanks to the camera head?
Yeah. I think yes, basically. It's not a super hard CV task, computer vision task, and I expect that with a very small computer vision open CV, you would easily be able to pick out these calibration tracks, find the one that is most well aligned. Because it's open CV, like you draw a bounding box, find the midpoint, find the one that's most well aligned. You know what you're expecting, and you kind of know what you're going to expect within those same bounds and the high contrast things. So yeah, as far as computer vision tasks, it's fairly trivial, but no computer vision task is actually really trivial. It's what every mechanical engineer says. It's like, oh, we'll solve that in software, we'll just put a camera on it and correct for it. So it's like when every mechanical engineer doesn't know what to do and they're kind of lost for an idea, that's what they always say. If you ever see a mechanical engineer saying that, you know that yeah, out of ideas. David.
Can I just mention, we looked at this problem sometime last year when we were doing IDEX. And in fact, we found we could use one of our IR sensors to measure the calibration markings.
Oh, that's neat. Yeah. And you mentioned this actually.
It's so easy to measure it, as long as the filament's white or some other high contrast material.
Yeah. So the Duet guys uses the reflectance of IR off of the bed surface to measure its Z offset. And yeah, basically, so you can treat it as a single pixel camera, and then you can go on because you can move said single pixel camera around the bed, effectively build up an image, and because you don't nearly have to do the whole bed, you can just scan along the line. You can figure out where these lines are quite easy. Others? Questions? All good?
One more. Do you have any plans on releasing with dual drive gears, except for the ones for this tool changing kit, like an upgrade for the Titan, for example?
Yes.
Okay.
Yeah. Not done yet. We mentioned Titan V2. It's still something that, but as I touched on before, 30 mass production, grip and force that's applicable, and be a really easy to use system. One of the things back when we released Titan, which was a long while back now, your best alternative was the old printed Wades extruder. And if anyone's had a printed Wades extruder, they really work, and they work very well. But once something goes wrong inside of them, they really suck to strip down. One of the things I was happiest with about Titan when we got it is you undo those 3 screws and then 4 screws, and you can take the front plate off and easily troubleshoot the whole system. Looking to replicate that, and if not have it even better, have the front door hinge and flick open so you can open the whole system up. Because let's face it, things go wrong inside of extruders, and lots of manufacturers, particularly printer manufacturers, do the disservice of not letting you get inside of the extruder. My pet hate is extruders that don't let you manually actuate them. I don't know if it's just me, and I'm too used to turning the gears on a Wades extruder and manually forcing the filament in and loading, and not being able to manually pull back the idler and just ram filament all the way down through into the hot end. And then it annoys me intensely not being able to get inside and having to go through some annoying touchscreen and press the load filament button and like, yeah, no, that's not what we're going to do. So yeah, it will be a nice extrusion system for people who like extrusion systems. Yeah. Any more for any more? Still got a few moments. No, all good? All right, thank you very much.
Thank you.